plus 1/2 q squared. Now, what would the total cost function be? Or, yeah, okay, well, let's keep it like that. So it'd be 10q. Okay. Plus there's already a 1/2 there, but you're going to, it's 1 over n plus 1 is going to be 3. So that would be 1/6. Oh, let's see. Oh, this should be 10q. I'm sorry, not 10 plus q. Sorry. 10q plus 1/6 q to what power? Q, yes. Plus a fixed cost. Now to make sure you've done it, just differentiate that total cost function with respect to q, and you get your marginal cost 10 plus 1/2 q squared. So it matches. Okay. Going from marginal revenue to total revenue. Marginal revenue is the derivative of total revenue with respect to output. So if you integrate marginal revenue, you get total revenue. Okay. If our marginal revenue curve was this, A minus 2BQ, what would total revenue be? What would total revenue be? What is the integral of this? A minus 2BQ with respect to Q. AQ. Right. Now, in this particular case, normally we would say plus a constant of integration. But typically, if output is 0, your revenue would be 0. So in this case, we wouldn't need a constant of integration under that assumption. Okay. So to verify that, just differentiate this. You get A minus 2BQ, which is marginal revenue. Okay. Okay. One more rather important example. The book has a few others, but I want to mention one in particular. Suppose you have a flow of revenue over time. And let's just write this this way. Think of R of T as being a revenue flow. Or another word that's sometimes used, or stream. In other words, let's assume that the flow of revenue is continuous. If it's $1,000 a year, that would mean, oh no, let's pick another number. Let's say, suppose the revenue stream was $12,000 per year. Then that would mean every 6 months the firm's revenue would be $6,000. Every month the revenue would be $1,000. And you could divide it into finer and finer parts. The idea is you get $12,000 over the course of the year, but that money is coming in continuously. It's a continuous stream over time. You're getting some money every day, every minute, every second. Continuous stream. Okay. In that case, the present value of the revenue stream over a certain period from, say, t equals 0 to t equals capital T, the present value of this revenue stream from t equals 0 to t equals capital T would be found as follows. You just take the integral. See, an integral is like an infinite sum. So it would be the integral, the present value. It would be the r of t times e to the minus rt dt from t equals 0 to t equals capital T. You multiply each of these instantaneous revenue streams by e to the minus rt. You add them up, means you integrate them, and that would give you the present value. Okay. There's actually a very neat formula you should remember or memorize if the revenue stream is constant over time. Suppose R of t is a constant revenue stream over time. For example, it could be $12,000 per year, but it's constant over time. So we let R of t be just some constant d. Then this formula becomes the present value of this revenue stream is just the integral from 0 to t of d times e to the minus rt dt. That would be the present value of that continuous stream of revenue d per year. Now, this is not quite in a form that is easily integrable, where we can easily find the integral. But we could, by a trick, make this into the right form. What would be the trick that we could use to easily find this integral? Well, you got e to the minus rt. What do you need in order to directly integrate it? Yes. Right. So what we need, Gray, is for this d to be a negative r. So how could we do that? We could do it, Gray, as long as we do what? What's that? You got it before. This is only slightly more difficult than the one you answered before.
So it's 1 over negative r d.
Yes, exactly. We pull this d out. See, we pull this d out. I think that was rule number 5 or something. It's a constant, so we can pull it out. But what we need is a minus r here, don't we? So we can insert that minus r there as long as we insert another one down here. And we need to make this a minus. Okay. Now we have it in the right form. Now we've got it in the form e to the f of t times f prime of t. So we can directly integrate this. And let me just write this minus d over r out here. And it's outside. And it's multiplied times e to the minus rt. And we're doing that from capital T is the upper limit to the lower limit is 0. Okay. So this is equal to minus d over r times, if you just substituted a capital T here, this will just be e to the minus r capital T. And then minus, if a little t is 0, then this will be what? 1. Okay. Now we could rewrite this, since I don't like that minus dr, we could write it as just d over r, just multiply by minus 1 twice. And this becomes 1 minus e to the minus rt. Okay. So it is a formula you can use to calculate the present value of a revenue stream, a constant revenue stream. Okay. For example, let's just take an example. I know you have your calculators with you. Suppose the continuous revenue stream is $1,000 per year. But this revenue is occurring at every instant of time. Over the course of a year, it's $1,000. The interest rate, continuously compounded interest rate, is 0.05. And let's let capital T be 20. So this kind of is similar, Ian, to the lottery problem. The only difference is usually if you win the lottery, say they make payments for 20 years, they usually give you discrete payments. The payments aren't continuous, but it's similar to that. So you're getting 20 years of this revenue stream, discounting it at a 5% interest rate, and capital T is 20. So what does this equal? Well, D over R will be 1,000 over 0.05. That would be what, 20,000? That's what D over R is. Times 1 minus E. This is 0.05 minus 0.05 times 20 would be minus 1. So if you calculate 1 minus E to the minus 1, and actually I did it all together. That's 0.6 something if you do the subtraction. So you get 12,642 and 41 cents. Okay. Makes sense. Because you're not getting the money up front as a lump sum payment, you get less than 20,000. So actually in the lottery, Ian, don't they have that option where if you win the lottery, you can get either a payment once a year for 20 years, or you can get it all at once. So
years, they take 50%, about 50% out after all is said and done, and then over the 20 years,
yeah.
they give you one payment and then increase it by 2 to 4% every year.
Okay. Okay. Well, this would be the present value if you took your lottery winnings as a lump sum payment. Now that's ignoring taxes. Usually if you win the lottery, they'll take out taxes too, but ignoring taxes, the lump sum payment, if you wanted it right away, would be $12,642.41. Okay. Considerably less, because a lot of your money is occurring in the future. And money received in the future is worth less than money received right now. Okay. So if you had a problem like this, and you get some figure greater than 20,000, then you know you made a mistake. It's got to be some figure less than 20,000. Okay. Okay. So this is a nice application of integrals, present value of a revenue stream. Okay. All right, that really finishes our discussion of integrals, unless you have questions. Okay. Why don't we take a short break, and then we will resume, and we will talk about the Kuhn-Tucker conditions.